We are group 6 from section 24. Today we are going to present a project data science for the title DDoS attack detection classification. Those are our group members: First me Hassan and Bahlul Nabil and Salahuddin Taha and Hussein Ahmed. For the introduction, DDoS attack detection classification project address the rising threat of distributed denial of service (DDoS attack). These attacks using network distribution through executive traffic pose of a significant challenge to online service suitability. The project aligns with the broader theme of from data to decision. Conducts a thorough analysis of DDoS SDN dataset, employing this descriptive, diagnostic, predictive, and prescriptive analytics. The project utilized data science and network analysis to understand predictive and propose strategy for preventing DDoS attacks. Through advanced techniques and machine learning, the project disease attack patterns, identify key predictors, and develops a model for anti-backing feature indicted. Beyond prediction, the project aims offer tailored recommendation to effectively throw DDoS attack, enhancing network infrastructure, reselling against such threats. For the problem statement, the problem at hand involved the rising threats of sophisticated distributed denial of service (DDoS) attacks within software-defined networks (SDN) environments, where traditional security measures face challenges due to the dynamic nature of SDNs. The dynamic environment creates vulnerabilities that malicious entities can exploit. The vast evolving nature of attack vectors requires advanced analytical techniques for real-time detection and response. The primary challenge is accurately identifying malicious traffic while differentiating it from being activities that may share similar patterns. For the objectives, the first objective is analyze the traffic patterns within the dataset to gain comprehensive understanding of normal various anomalous network behavior. The second objective is identify characteristics and the patterns associated with DDoS attack, distinguishing them from being traffic. The third objective is implement and refine predictive models that can accurately classify network traffic.
Assalamu alaikum warahmatullah. This is Hussein Ahmed and thank you, Ammi Hassan. So for this part, for descriptive analytics, in this section we provide a comprehensive overview of the dataset SDN data pointed from Kaggle. So serving as the basis for our software-defined networking analysis. The dataset comprises 104,345 rows, records each representing a unique network interaction, and 23 columns. So our goal is to classify traffic as normal or not using classical machine learning algorithm. This analytical exploration aims to yield valuable insights into the dataset structure and nature, providing our subsequent offers in advanced analytical and anomaly detection. So here we have the data frame head, and this table displays the first few rows of the dataset, reflecting the format and variety of data points that will be analyzed. It provides an immediate snapshot of key columns such as source and distribution IP addresses, packet and byte count, and flow duration, which are crucial for understanding the initial state of the network traffic data. And for the dataset structure, this table displays the data type of each column and the count of null values, which is fundamental for initial data assessment. This comprehensive overview aids to identifying any immediate data integrity issues, such as missing values that could impact the quality of the analysis. And for the traffic classification frequency, the count plot visually represents the distribution of traffic classes, benign or malicious, in the dataset. This visualization is crucial for assessing the dataset class distribution, ensuring that predictive models are trained and representative sample for effective network security analysis. Here in this plot, we see that the label contains Boolean values, 1 for benign and 0 for malicious. So here we have the benign face malicious traffic proportion. So in this plot, we have the percentage of benign and malicious requests in the dataset. This pie chart visually represents the dataset definition into benign and malicious requests, offering a clear view of the prevalence of each traffic type. This proportional breakdown is essential for assessing the extent of malicious activities in the network. So for the statistical distribution of network features, the summary statistics table provide insights into the dataset offering measure of central tendency and variability for each numeric features. It aids in early detection of outliers, error, and anomalies, and provide an understanding for typical values and range for network attributes such as average flow duration and packet count. Here we have the non-values across dataset. The output quantifies missing data in each column. A crucial step for subsequent analytics reliability, identifying these gaps inform the data cleaning strategy. So for the detection of anomalies in network traffic, here we detect anomalies in network traffic, especially focusing on unusually high packet count. It calculates the main and standard definition of the BKT count column in the data frame X, an anomaly threshold and set by adding 3 times the standard definition to the main. The code identify potential anomalies by selecting rows where BKT count values surpass the threshold and prints details of these anomalies. The particle approach helps recognize unusual patterns in network traffic, indicating potential issue for security threats. So for the pattern recognition in those attacks, the station focusing on identifying patterns in on malicious network traffic, particularly those attack. It calculates and brings the main characteristic of pattern features, offering insights into the typical behavior observed in such attack. And for the packet rate between malicious and benign network traffic, the table display an independent t-test to compare packet rates between malicious and benign network traffic. It computes the t-test and p-value with a threshold of 0.05. If the p-value is below 0.05, then the null hypothesis is rejected, indicating a significant difference with a malicious traffic having higher packet rate. Uh, P-value of 0.05 or higher suggested no significant distinction in packet rate and the null hypothesis stands. So here, as you can see, we have the request distribution across protocols, and we have the three protocols, which is TCP, UDP, and ICMP. And this part illustrates the distribution of network requests by protocol type, and it helps to identify patterns in protocol usage across both benign and potentially malicious traffic. So last and not the least, request frequency based source IP address. So doctor, actually for this part we had put in our report this part as three graphs or three plots. So each one represent its own meaning. For the first graph, we have put the frequency and distribution of all the requests in the network, and then in second graph we have put or appointed the malicious distribution of network requests, and then for this graph we illustrate the frequency and distribution of network requests from different source IP addresses with the malicious. So as you can see here, as the blue is for the malicious and the green is for the all or the request in the network.
Diagnostic analysis. Analyze and visualization were conducted in this section to explore a software-defined network (CDN) dataset. Initialize focus on missing data we followed by visualization like histogram, frequency distribution, and statistical profile. The study delved into temporal aspects, data volume, switches engagement, and highlighted characters' main values for the DDoS attack. Detailed statistical analysis of packet rates distinguished being from the malicious traffic emphasizes the importance of diagnostic analysis in identifying and responding to cybersecurity threats in CDN environment. Histogram of traffic flow duration. In this histogram, it shows the duration and data flow. So the axis shows the time duration by a second, and the y-axis shows the data flow. So for the diagram data flows, different normal user behavior from potential security incidents by division and duration range. The second histogram of transmission bytes, which is TX bytes. The transmitted bytes histogram provide a diagnostic view of data flows, aiding to identify anomalies such as unusual high or low traffic, as you can see in the red side. So these divisions may signal technical issue or security threats, including data breach or the DDoS attack. In this graph, which we call switch interactions. So in this graph, it provides a diagnostic analysis of network switch engaged with the traffic flows, and it will identify the frequently used switch and potential overboarding. This insight is critical for diagnostic network load distribution. So it will guide and capture upgrades and potential switch suspicious to network attacks. Frequency distribution of malicious traffic across network switches. So as you can see in the figure, we have the switch and we have the values. So this uneven distribution signals verifying engagement levels visible, indicating targets attacks on specific network segments or vulnerabilities in certain switches. This information is vital for network diagnostic and information that develop or target defensive strategies such as strength security protocols. This figure shows the characteristics main value of network features in the DDoS attack. As you can see, TDI, it has the value of 1.6 and the other. So if we focused at the most valuable one or the most one, it has the value, it's RX kbps and TX kbps. And the lowest one, which is the labeling, which has the frequency of 1. So in this part, we do statistical analysis of packet bits between traffic types. So in this part, in the summary of it, we did a hypothesis testing. So we get the value of T statistics and B value. So the T statistics, it shows as minus 27.83 blah blah blah, and B value it's 1.22 blah blah blah. So in the hypothesis testing, we summarized higher packet rates in malicious traffic. So that's what we get in the statistical analysis. So as you can see in this figure, we do the anomaly detection in network traffic. This table displays flagged anomalies in network traffic, focusing on rows labels 1 for potential malicious activities. It includes key features like packet count, byte count, duration, packet rate, network switch source, and distribution, IPs, and protocols. Those anomalies shows the division like high packet counts or transmission rates or suggestion cybersecurity threats such as the DDoS attack. It shows details traffic flow, offering essential metrics for diagnosing and understanding anomalies, guiding further investigation to confirm malicious intent and plan appropriate responses. Here in the evidence of elevated packet rates in malicious traffic. So after we do the hypothesis, we get the result. So the results of our hypothesis, we reject null hypothesis. Why? Because the malicious traffic has significant higher packet rates than benign traffic.
Okay, I will continue in this part for the predictive analytics. So evaluation of logistic regression model performance. As you can see, Doctor, here in the left, we have the logistic regression model without feature selection, achieve an accuracy of 76.64%. And here on the right, we have the support vector machine model accuracy and metrics. So the CVM model processed without feature selection accepts the first accuracy levels based on the kernel employed, multiply usage, and RBF kernel. The model achieved a big accuracy of 97.0%, emphasizing its robot classification capability. So for the decision tree analysis, the decision tree model initially tested without feature selection and later defined through hyperparameter tuning using methods like grid search with cross validation. Demonstrate at impressive accuracy of 98.22%, showcasing strong predictive capabilities in classifying network traffic as benign or malicious with high confidence. So now I will let the next presenter continue.
Outcome improved network security that insist and productive model contribute to strengthening that security measure in place CDN environment. Strategic mitigation that Prescriptive analysis component provides strategic recommendation from proactively managing identify threats reflecting potential downtime. Rich contribution that find over variable comparisons to the research, particularly in the context of SDN. Scalable framework that establish analytical framework is scalable and adaptable, providing a base from feature expansion and enhancement. Conclusion, we estimate DDoS attacks on software and network are analyzed include understand normal behavior, speeding issue, and predicting future attacks shall affect model like logic, regression, SVM, and discussion trees. This help bots supporting on SDN, ensuring quick detection and provision of DDoS attacks from a source network feature work could inform real-time model integration and advanced feature development, advanced network security through machine learning. Want to say thank you for your attention. Group number 6, section 24.